talking about the last of our completions. Mr. Cox and Mr. Brewer, I have two of these. Let's take a look and see what we've got, because we're going to finish up fairly quick on completions and then start going into production. Depending on how far we get on production, we may get as far as pipelines. If we get as far as pipelines, I probably will show one film, though I don't think we would have time for two films. I've got, if that's the case, the second one takes about 60 minutes, and I may do that on the next class, and then we take the test after the film. So we do have a quiz next class period. Y'all remember that, right?
Yeah. Absolutely.
Is that just from recent lectures or totality?
No. It'll just be the sections that we've
Okay.
finished up. No, it won't encompass the whole thing. That we already did it over the first. I didn't bring a syllabus with me. I can look one up real quick. But we already did the. I think the first 4 weeks, 5 weeks. So this will be over the next part. This will be over drilling, offshore completions, and then also on some on production. But before I verify that, let me check something real quick, and I'll tell you exactly, because I don't want you to study stuff that's useless for you to study. Hang on, I'll tell you. As soon as this comes up, I'll actually show you.
Weeks 5 to 10. Oh, thank you. You shouldn't have.
Push this thing too hard. I didn't want to take my disc. Oh, there. Now it's all right. Okay, so if we take a look right here, let's see, 160. Okay, first quiz was over 1 through 4, that's what I thought. Okay, so the second one is over 5 through 10, and we will be starting into 10 today. I don't know that we'll probably cover quite a bit of the well production, secondary, tertiary recovery, things like that. The quiz will not include anything to do with offshore transportation, rail, trucks, or any pipeline. It won't have that, but it will have everything 5 through 10. So 5 through 10 covers everything from drilling, okay, there'll be some drilling, some things on drilling, but we pretty much covered that on our last one. I had you do the drill rig and all that. So this would be more on offshore, and then it would be on well completions, casings, wellheads, things of that nature. Some of the things that we've been talking about, well production, and then getting into our secondary recovery and that type of nature. Maybe more of a limited quiz because we are just about half a class behind where we'd like us to be. And so, but I'm not going to delay the quiz. I want to get it out of my hair so that we can go ahead and keep focusing on some things that we need to cover. Because we need to move on into emulsion, natural gas, and some of those types of things. So, fair enough? So you may have just a quiz, not even a test quiz.
Wow.
Yeah. that was
Jeremy,
good.
I don't believe you, but that's okay.
I know you're skeptical. I can see that. Yeah, really, I don't believe this. I mean, I can admit lots of questions, but I did give a whole different kind for operations today. I gave it in the simulator, so that was they didn't even have a paper quiz. But then they finally they realized what they did to themselves. So I don't know if they're really as happy as they wanted to be.
It's like your take-home quiz.
It was fun.
Well, they realized that they took everything off of quiz 2 and moved it to the final. The final's already bad. That final's going to be worse. I don't pull any punches on operation. I tell them first day in class, right? I tell you, it's a bad final. Okay.
Define bad.
What's that?
Define bad.
Define bad?
Not good.
I've actually had 2 people in the last 8 years got a 99 on it. But both of those people went down south, tested out in refining jobs, and out of 800 people scored number 1. They were extremely sharp. And I've had people, I'm not going to say they cried.
They did. You told us they cried.
I know. I did.
What?
No, it's awful. And so,
Especially if you've made it through that far and you pick your GPA up and then you get to that.
yeah, it's like, well, it's like signing off for an area. Okay, so let's go down. We were talking about specifically surface safety valves and subsurface safety valves. I want to go back and revisit that a little bit. This is about where we ended up. This is actually a good example of a surface safety valve, and I want you to think of it in terms that it can be, this is coming up through with your production like so. This would be your hydraulic actuator. Let's go back and look at a Christmas tree so you can remember what you're looking at. Okay, I'm going to call up our little red Christmas tree. I think I had it right. This may not be the diagram. This may be actually a Christmas tree. I need the diagram right here. So when we're talking about our surface safety valve, I'm going to show you the other picture here. And you're going to be looking at where the well flows through like so, and then you're going to have your hydraulic actuator, which then is going to apply pressure so that it is opened up. And that's what you're looking at here, is it's going to be pushed into the open position when you've got your hydraulic fluid. It's going to go ahead and open it up so that you are over this way and you're actually flowing through. You've got this valve that comes across, a nice flat valve that's got a hole in the middle of it. And so what will happen is you'll flow up through there, but if you lose your hydraulic pressure, it trips out. The spring will cause this thing to slam shut. When it does, it stops all flow, just abruptly. Okay? These are usually, I'm not going to say usually, they can be mounted this way. They can also be mounted off your tree on on an arm coming off, and I don't know if you can see that real well right here. You might be able to, let's see, I think on the, hold on a second, this was out at, no, I thought maybe the ones at Swanson River showed, this actually showed them. And they had, this was a dual completion. We talked about dual completions. No, this didn't have it either. I thought that one of these had that, but it doesn't. Yeah, that was, I'll leave that up because we talked about dual completions. I'll come back to it. Hang on a second. See if I got it. No, I don't have a real good photo of that where I can show you, but sometimes coming off of the arms, your main production will come on up and then it'll be like so, and then over here, I thought I had one at Swanson River that I could show you on production on a tree at Swanson River, and it shows very, very well the on the XTO. Yeah, you can't see it well enough. The Swanson River picture shows it real well, and I don't have that available right offhand. It might be under my production side. And so what you have is, let's go back and take a look then. What you're going to have is, like I said, you're going to have a pilot valve that's going to come off if you're producing off of your well. Remember what we're seeing right here, and I'll go back to your tree so that you can see this, and I want you to picture this in your mind. Is when I've got a tree that's going down, if you recall, this goes down to my wellhead, okay? And then on down into my casing and on down into my well, and then we come all the way up to my tree where I can then begin to control the flow out of my production line that's coming up. And I've got my master valve. You're going to see a tree today I'm going to show you in a little bit that's going to show two master valves, upper and lower. And so then typically, I'm going to have a surface safety valve that's going to be in line in my tree so I can stop all flow. But sometimes this comes right up like this and goes into my crossing, right into an arm. There is nothing else. And so then what I might have is I might have it over here where I can go ahead and block all the flow in, which in essence is going to do the same thing. So it doesn't always have to be mounted like this. This is the point I was trying to make. And so when you think of this and it looks like this could actually be on one of my production arms, and it could be mounted like so, and it would just look different, is what I want you to see. It can look different than what you might be expecting or anticipating it to look. So when you go in the field and someone says, well, there's my surface safety valve, and they can be made up differently than what you see also. They don't necessarily have to be long and skinny like this. They might have a real short, round type of a diaphragm system that can be very powerful, but it isn't long and skinny like that. All of them, though, however, will work essentially the same way, where I'm going to have some kind of a system that downstream, coming off of my production valve and off of my wing that's out here, on my production wing, is I'm going to have some way of sensing the pressure that will trip apart, will affect the pilot valve, that is then telling the hydraulic, my hydraulic system to go ahead and keep this pressured up. I put it into service, that when this trips, it tells that hydraulic to either bypass and take the pressure to zero, or it's got a hydraulic pump on it that tells it to go to zero. It trips out one way or another. All the hydraulic pressure comes off, or pneumatic pressure if you're using air, and then this is going to slam shut. That's what we're really looking at. So I want you to see that. It's important to know. Now, what was the bad thing about surface safety valves that we brought up last class period, just to review so we can move on?
They're
People with,
useful for people who you don't want to see.
C4 could blow them up.
If something's wrong with the Christmas tree, like, for some reason, when it gets blown off, there's nothing to stop the rest of the oil
That's right.
from coming out.
These are only as good as from where? Where is this secure?
From the safety valve.
Is it secure from here down? No, and I've got this very dangerous place right here, which was proven in Kuwait. Remember the Kuwait fires that I showed you guys a little bit last class period? I think I still have those up. Hang on, I'll show them again. So that and that was these fires in Kuwait right here, and which Saddam Hussein in the first Gulf War blew up. As he left Kuwait, he blew up all the Christmas trees to try to eradicate their oil fields. And he did a pretty good job of destroying a lot of oil. They were all free-flowing. Okay, and so to alleviate that problem, the state of Alaska looked at this, and nationwide also. Hang on, we'll open this up a different way. State of Alaska instituted rules that they started using subsurface safety valves, which means that when you go down the well, and if I were to draw this out, somewhere down below, and I think this is about where we ended up last week, is if this is my Christmas tree up here, maybe this will let me draw. This is my Christmas tree up here, and I'm coming down in my well all the way down below the surface, anywhere from, say, a few hundred feet to 1,000 feet or more. I'm going to have a subsurface safety valve that I'm going to mount in my production line. I'm going to be down below down to a place where this is secure, and if it blows out, it's not going to blow out and go into the formation into my water zone or anything like that. In other words, if I even had a blowout in the line down here somewhere, maybe there was an earthquake and it messed my production line up, then this would go ahead and shut, and it would keep me from leaking into the water into the water strata or anything like that. So there's a lot of advantages in having these at different levels. In the North Slope, they are anywhere from 500 to 1,500 feet down or more. So it all depends on the well. But in Alaska, over water, any gas well has to have subsurface safety valves. Any gas wells on land have to have subsurface safety valves because they're always free flowing. Okay? And this is just general rules. It gets very much specific anymore because there's been some qualifiers put in. But you can assume all gas wells, and then you can assume that any oil well over water that is free flowing is going to require a subsurface safety valve. Now, it's not that way necessarily on land. It depends on, they've changed the rules to where it has something to do with being adjacent to facilities or buildings and different things like that, where if it caught fire or something, it could actually cause some destruction. So there's some real specific rules now. It's not necessarily universal just because it's on land. On land, it's considered that it's easier to go ahead and obtain access to put the thing out if there was a problem. So, I don't know that I agree with that. I think that all free-flowing wells should have these, but they do cost money. Why do they cost money? What's the reason anybody can see right here? It would cost money to put one of these in.
They look complex.
You gotta put it down hole.
I have to put it down hole. What's it take to put this down hole? Can I do it with a wire line?
No.
It's gotta be.
Yeah, you gotta pull
You're gonna have to pull
the
the VOP.
I have to pull my production string up. I have
Right
to
in.
fit this into the production string, I have to run hydraulic lines down, I have to assure this is working correctly, then I have to have a Christmas tree and a wellhead up above that will accommodate that line coming through it. Almost the same as if I had a ESP, okay, same kind of thing. I've got to have some way of getting through that wellhead and that Christmas tree. So these are expensive to put in, and then you have to work with them, and if it fails,
Uh-oh. You have to drag it out.
I have to get a workover rig in, and I've got to pull all of that string back up, service it, and put it all back down again. Is that costly? Yeah. A lot more than if it's just up there on the surface. So those are some of the considerations. Let me erase this. I think that about catches us up where we were at. So let's start changing direction here a little bit, literally, on horizontal wells. I didn't mean to be making a pun. I just realized I did. We're going to look at some horizontal drilling and completions. And so I'm going to go ahead, we'll talk a little bit about this, and then I'll show you, I've got a one or two videos that I think would be real good for this. And so when we're talking about completions on horizontal wells, this is classic for Marcellus Shale. It's not a very big picture, but let's take a look at some of the, when we're talking fracturing, we're talking about going down into we're talking about coming down into our zone, not so much, I'm not referencing so much the horizontal drilling. We've gone through horizontal drilling a bit. But we're talking about fracturing down into, this is completion. This means that I brought my well in, but now I want to make certain that I've got good production. Okay, so the way that I get good production, and especially in tight formations, and it's not something new, it's been around for a long time, is I go in and I fracture the zone that I'm in. When I say fracture the zone, there's a number of ways of doing that. One is I use high pressure water. Okay, I literally will take water at a very high pressure and I pump it down into my well, and I literally am forcing that out into the formation, and I'm at such a pressure that I'm cracking the formation. Now with your Marcellus Shale, what that'll do is it will make all kinds of lines just like what you see, and this is what it does. I think I've got a better rendition of this. Hang on just a second right here. This is a well before and after fracture is what it would look like. Before fracture and after fracture, in which you actually would increase the roadways, if you will, for oil to begin to seep in. These just being little bits of oil. And when we're out walking my dog, and I think I ended up with more hair on me than I did her. You know, see all these hairs in my eyes. So part of this fracturing, and there's nothing magic about it having to be a horizontal well. Fracturing was around when we had when we had nothing but just vertical wells, and we would fracture formations. And then when we got into deviated wells, we'd fracture formations. But now it's really good for these long horizontal completions, because if I fracture and then I've got these long completions, I can take what were marginal oil wells or gas wells before. I've made a long highway, and I can begin to pull it in. So I use high pressure water. Sometimes I'll use what's called proppants. Just a minute, I'll show you what I'm talking about. Proppants are literally frac sand. And frac sand, or the term proppant, I don't know if that's an A-N or
It's an A-N.
Probably an A-N.
Yeah.
Proppant. Okay, who said A-N?
I did. I've read it.
Proppant. Yeah. I get my E-Ns and my A-Ns confused. Proppants these originally were real sand, and what it was intended, and now they are made out of a polymer, real hard, extremely hard polymer. When I say hard, we bought a bunch of this used stuff when I was running a sandblasting business, and we were using it and then recycling it, and we can't destroy this stuff. Terrible sandblasting medium. that has no jagged edges on it. So all it did was just like a little bead blast. And, but you'd recycle it, there was no dust. You'd recycle it, no dust, because it doesn't break down. In fact, you can't break the dumb stuff down. It just is so hard, it's as hard as a diamond. And you can't cut it, you can't smash it, you can't break it, you can't do anything. And that's what it's intended to do, is to mix it with the water, under high pressure water, blast it into your formation, little minuscule bits of sand. And what they do is they keep little areas of the formation open to open up the formation so that you increase the permeability. Okay, it's not that I'm making spaces for the oil to be there. The oil is there, it just doesn't travel well because it doesn't have good little trails to travel on. So you jam it with frac sand and high pressure water, and you fracture the formation, you blow this stuff back in there, you create these oil highways, and then you increase the production. The other way that you can do is to also take and use acids of different types of different chemicals. The acids will literally go into the formation, and what they do is they begin to etch and eat away at the rock, and they open things up. Okay, any minerals that can be easily dissolved by the acids will then open up these highways so that you can go ahead and, hang on.
Henry, you can't promote porosity the same way you can permeability, right? You cannot do that. It's either there
You're
or
either porous or you're not.
not. Right.
The only thing that you can do to, no, you can't, you really can't do anything with porosity. That's determined strictly by the material that you're in. But a lot of times we have material that is present, pretty good porous material, but it has no way to travel. It has real poor permeability. So what we're trying to do is to increase that permeability. This gives you an idea. Here we've fractured it with high pressure water. Here we've added the proppants that will then tend to open it up. Now, if I put chemicals in with that, then what I'd be doing is eating this up and eating up little pathways that come into these areas that I have made. And so that's what I'm looking at. But don't think it's great big avenues and holes in the formation. It's just a shattering. Anybody ever had a windshield break because of cold weather?
Spider cracks.
Yeah, just spider cracks everywhere. The same thing, that's what you're looking at, is these immense cracks and trails all over inside the formation. And don't think just in a horizontal plane, think 360 degrees as far as three-dimensional. It's like everywhere, like one great big huge mass of roots going into the formation.
The more the better, I would imagine.
Yeah, it is. And up until you get to the call where it's too much cost. And it is very costly because what we're talking about is a lot of equipment, a lot of high water. A lot of the water is reused now because the water is, has got a lot of cost value, especially when you start getting into places like West Texas or New Mexico and places where a lot of water is not available. And then you're using frac pumpers, which are big triplex pumps and maybe multiple pumps where you've got a lot of pressure, a lot of volume, and a lot of hammering to get this pressure up and push it into the formation. You're pushing material into something that doesn't want to receive it. And so it cracks and shatters to receive what you're doing. You know, a lot of people talk about, well, we shouldn't have fracturing back on the East Coast because it's caused lots of problems. And it has caused problems, absolutely, because of careless regulations and careless oversight on the part of the different state governments when it first started off. All of this Marcellus shale and some of the oil, shale oil and things like that, that nobody was watching what was happening, and people were going down and just drilling down very shallow near the water zones, near your water formations, your aquifers, and so then they were going ahead and fracking, and now gas was intermingling. What did we find when we don't have good casing? Things will go and flow from one area to another, and a lot of these were run without any casing. They were not just barefoot completions, they were completions without casing. And so then what you had is a tremendous intermingling of water, natural gas, more natural gas problems than anything, so that literally what you hear the horror stories of people opening their spigot for their water and their water would actually catch fire, that's true. There was gas, enough gas coming out of their water that they could torch it off. So here you've got a faucet, you put a match to it, it burns, now I've got hot water. No.
I was about to say, you get rid of your heating.
That's,
So the only reason fracking has a bad name is because people being careless and dumb.
yeah, and a lot of that's under control now. It really is, serious control. And there's been a lot of regulations that have been put in. If you read in a lot of your news, fracking's been going on for well over 100 years in California. It's been going on in Texas, New Mexico, all through the Midwest. Here in Alaska, it's been going on for almost 100 years, and there was never any problems. It was where it was very, very loose, and it was a boom mentality situation, and people just took advantage of it for a few years. Gave it a bad name, but it's pretty well settled down where most of the problems they talk about now, I would say 99% of them are from prior years. And so it's pretty well settled down, and it's well under control and oversight, but it wasn't in the beginning. Just like we read about oil discovery in the beginning in Pennsylvania, and what they do with all the leftover oil went down the creek, you know. Well, that's not such a common thing anymore. It's not supposed to be.
Henry, when they're fracking, from what I read and looking around, they're saying they're only recovering 25 to 50% of the water or stuff down there. Where's it going?
Into the formation.
Just gone, huh?
Yeah.
It's not retreating back into that.
It'll eventually recover, but it'll be in the entire time you're producing. So if you're looking at a 40-year production well, it'll take that long to recover it all.
The fracking water.
Because
Yeah.
that makes sense with everything else.
Yeah, it literally, I don't want to say homogenizes, but it goes into the formation. It becomes a part of the formation. That's what actually happens. And so, yeah, no, that's true.
You're using that to pressurize the formation, the water.
What?
Ask your question,
fracking,
Harley.
yeah, that's right. I was trying to follow the fracking thing.
What's that?
So the water is used to fracture the rock by putting it in at high pressure.
Yeah, you use the water under extreme high pressure to go ahead and crack the formation, shatter it, if you will. That's the best way. But like Mike just brought up, upwards to 50% of that
It's gonna
water,
leach out.
it is forced back in because that's where it's cracking. Then we recover quite a bit of it, anywhere from 25 to 50%, maybe a little higher. But then that water is reused, but we've lost that other water.
And the volume of water they're using was astounding.
I can imagine.
A lot of volume,
They were talking,
millions.
yeah, okay, I was gonna say millions, but I didn't want to sound like a lunatic.
No, that's right. Millions of gallons and push and pumping and pushing and pumping and pushing, so that once it starts to crack, you push that crack until it doesn't go anymore.
Okay.
So is that impact or pressure that's gonna do that?
It's a number of things. One, it's that it's that impact of breaking it. But
Right.
then once, anybody in here ever pushed a car, but it was slightly uphill and you wanted to get it going, or you just pushed a car, a big heavy one, and it took 2 or 3 of you, but once you got it rolling, then you wanted to keep pushing to keep it going to where you could get it up to speed. You didn't want to stop. Is that right? Am I correct here? And that's how it was when I was out of gas and trying to push my car. Think of the same kind of a situation here is I have literally broke through that resistance, that first resistance. But once I broke through that first resistance,
Keep your momentum going.
I will know when I do, because what's going to happen to my pressure up here? It's going to start to go down. You know that from the fire department. So my pressure is going to start to fall. I need to kick that pressure up and really begin to push, because now what am I doing? I've got cracks that are starting to form, and I want to follow those cracks out until I finally reach the end of where I'm going. And then as I'm cracking here, I'm going to have side cracks. I'm going to have side cracks off the side cracks. I'm really starting to shatter. And so I'm going to go for, it's going to come down to an economic cost. How much do I want to do? And what have I determined, the reservoir engineer, what have I determined it's going to take in that particular formation to achieve what I'm trying to do. The first few are going to be real experimental. The ones after that, I'll know the formation. But yeah, I'm going to use a lot of water. Now, when I get to that point, I pushed a lot of water way back in here somewhere. And no, I'm not going to recover. I will recover it. You know, let's think of that differently. I won't recover it immediately, but I will recover it. It's just that it will take years in some cases. The other consequence is that I may have a higher content of water in my oil and gas production than I would have had previously.
It's obviously not potable water, but is it hazardous?
It's hazardous, yeah, absolutely.
It's chemicals?
Oh,
and everything else?
absolutely,
Okay,
yeah, yeah, because I'm going to have acids in it, I'm going to have
Okay.
different chemicals.
Okay.
And so that brings up this next question. Where am I doing this at?
Yeah,
At
exactly.
what level in my oil well?
Linear production.
So if I've got a, let's take one that's not real deep. We talk about 10,000 feet here, but let's say we're 7,500 feet. Am I going to have my potable water aquifer at 7,500 feet down? Possibly, probably not. You know, there's probably going to be clay layers in between. And if I did have a viable aquifer at that level, I wouldn't be allowed to.
EPA wouldn't let you do that.
No. But if I'm at, say, around here, and there's been a lot of hydraulic fracturing going on here for years, if I had, and nobody even knew it, but if I had, was fracturing at 10,000 feet, is that going to affect my drinking water? Probably not. Who in here has wells that go down over 150 feet? Anybody?
I think our low is like 26.
Yeah, the wells for Agrium were at about 350 feet. Chevron's wells were at about 300 to 320 feet.
You're way out of range.
And those were considered deep wells around here, and they were massive producers. I mean, there's a river down there that you can't believe. You can pump all the water you want. We were pumping right about 950, 1850, 19, about 2,500,000 pounds of water an hour at Agrium.
Oh my gosh.
Out of about 4 wells, maybe 5. That's a lot of water. But it was from just 300 feet down. Harley?
That's the thing, the reason we probably pump so much water without drying up the reservoir or whatever is probably because we're on a sedimentary kind of area, basin, right? And which is pretty absorbent. And we've got this inlet just right there, and it's probably just gravity feeding water.
Lots of water, and we've got a lot of snow melt off our mountains. Now, some places don't have that. You get down in West Texas, and there's a lot of concern, because you have the Ogallala Aquifer, but there's a lot of people drawing water off of that, and they're using it for what? You've been down in Texas.
Agricultural irrigation.
That's right, irrigation,
Gross.
drinking water, things like that, and everybody's using it. Now, do I want to go ahead and have people doing fracturing that are using vast amounts of water with no recovery?
That'll piss
No.
people off.
Yep, it tends to make them really upset, that's right. And so right now what they're doing, and Mike brought this point up, and it's a good one, is that they are requiring a lot of recovery, as maximum recovery. They put it into these rain for rent type tanks, move all the water to the next facility that they've recovered, and then there's some sort of a price to pay for the fact that they used up water that they didn't have. They also have to have water rights to obtain that water. I mean, there's actually been talk about going ahead and purifying seawater to use as a water injection source. And so,
Desalinization.
yep, so there's lots of different ways of doing that.
You can't just pump the salt water in there, I don't want that.
Well, no, you clean the salt water up.
Corroded.
Yeah, you don't want to start putting salts down there, you're going to make hydrochloric acid, you'll have all kinds of mess down there. You don't want to do that. So you have frac sand type well before. Let's take a look at something here. I think I may have shown you this one film before. I'm going to show you a couple. And these are good educational videos. I know how much you guys like videos. I like videos. I gotta decide whether I'm gonna do Chesapeake Energy fracking. That's really kind of an advertisement, or I've got another. I don't think I like the animation. We'll go with Chesapeake. How's that sound? It's a little bit of a, we're Chesapeake and we're really good, you know. You guys will have to bear with it.
Little propaganda.
Huh? A little, well, it's not as bad as the marathon one I have, man. It's serious, some serious propaganda. What is this? You checking add-on compatible for this version of Fire? I didn't want Firefox.
You're off in a rabbit hole.
That's just where,
Rabbit trail.
that's just what's gonna open. There it goes. It's going now.
Okay. So, where do I came up that way? Well, this isn't too bad. They got 160.
In order to maximize the production potential of the well, the shale formation will be hydraulically fractured. In preparation for the fracturing process, the casing will be perforated in the horizontal portion of the well using tubing-conveyed perforating guns containing explosive charges. The perforated intervals are spaced approximately 50 to 80 feet apart and create a connection between the production casing and the shale formation. With the initial perforating complete, the tubing and perforating guns are pulled to the surface, and the workover rig is replaced by a hydraulic fracturing crew consisting of a number of high-pressure pumps and blending equipment. This equipment will pump a mixture of water and proppant, usually sand, through the newly created perforations in the production casing and into the shale formation. First, water is passed from a water storage impoundment into the blue working tanks depicted on this location. The water is then pulled into a hydration unit, which provides the ability to gel the fluid before it is transferred to the blender. At the blender, proppant and a small amount of chemicals that aid in the fracturing process are added. The blender transfers the fluid and proppant mixture to the pump trucks through the low pressure side of the manifold. The fracturing pumps increase the pressure of the fluid, sending it back through the high pressure side of the manifold to the fractory where it enters the well. The entire fracturing process is controlled from the treatment monitoring van. When the fracturing fluid reaches the perforations, pressure builds until the shale formation fractures, allowing fluid to enter into the formation. Additional fractures are created along natural zones of weakness in the shale. These fractures are contained within the shale formation, well below the ground. After an initial stage of fluid called the pad is pumped to create a fracture area, proppant is added to the fluid and is distributed throughout the newly created fracture network. At the conclusion of the fracturing treatment, the proppant allows the fractures to remain open so that the natural gas can flow into the production casing and to the surface. This completes the first of several stages in the fracturing process. This process is repeated by lowering and pumping down an isolation plug and perforating guns into the wellbore to complete the next stage of fracturing. This time, the tools are conveyed into the well by a wireline unit, which allows the fracturing process to proceed much faster and more efficiently. A lubricator is used to control the pressure of the well while the operation is taking place. On the bottom of the perforating gun, a composite bridge plug is placed to isolate the newly fractured zone. This ensures that the subsequent fracturing treatment is contained in the current zone. The perforating gun is again fired at roughly 50 to 80 foot intervals, creating a connection between the production casing and the shale formation. The fracturing process is then repeated until all of the stages are completed. A typical shale well has approximately 8 to 12 stages of fracturing. At the conclusion of the fracturing operations, the isolation plugs are removed from the well and production can start. The produced fluids are diverted through a flowback manifold into storage tanks. The fluids are then recycled or disposed of according to state and federal regulations.
That help a little bit?
Well, those, without the proppant, those fractures will naturally reseal?
Yeah,
That's
absolutely.
period.
Yep, they will reseal. Now, There was an acidizing that they used to do in the old days, which would help to eat that out and help keep it open, but they still would tend to reseal. The proppants make a huge, huge difference. And so I wanted you to see that, and that's part of what the
Henry, when they're
proppants are.
pressurizing that casing and all the way down to the perforated areas, is the entire well casing under that pressure, or? is
Yep.
it- Okay, so I guess that's where one of the concerns is if you have some integrity issue up higher in your casing, you could be losing.
Boom.
I mean, into water systems and things like that, and you're not, I mean, if your pressure's decreasing, you think you're just kicking ass on the bottom of the hole.
And you're actually,
Right.
that's right, and that's one of the big concerns, is you'd want to test before you go and do any kind of hydraulic fracturing, you'd want to know that the integrity on your casing was in good shape. You may want to have it tested first.
Hydrostatic or something.
Actually do, yeah, a hydrostatic test of some sort or
Oh,
another. And you can do that, because if you've got your casing, you've got your annulus and those different, and you've got your production string, you can go ahead and do a test, see if you have good integrity, no leaks, where your joints are, things of that nature.
Okay.
No, that's an excellent point. And those are things where you would think that you were doing really well, but you're not doing well at all. And I don't know if that's one of the causes for the leaks in the water. Most of what I've read is that has not been the cause. The cause has always been, it was just trying not to have to pay the expense of casing,
Right.
different things of that nature.
Well, nowhere have I seen anywhere what kind of pressures they're actually pushing, but it's, I mean, it's got.
I haven't really got a feel for the pressures. I can't give you, it's just not mentioned. And I don't know if it's proprietary or what it is. But you know, to shatter a shale formation, you're gonna have to be somewhere between 5 and 10,000 PSI. And those types of trucks, those triplex drivers, I used to operate triplex pumps out on the Dillon platform. We drive them with 1200, actually they're 1153 Waukeshaws. And those were pretty good sized Waukeshaws. And then we also had some 1250, they weren't Waukeshaws, they were another type. I know they weren't Cummins, but anyway, we would drive these triplex pumps and we would pump as high as 5,600 PSI for putting our water flood back down the hole. Well, that was just with some small triplex pumps, not like what you get on some of these big, huge trucks where you're either pumping mud or you're pumping frac fluid down, gelatin, that water gelatin material, things like that. So I'm going to estimate that they're probably 8,000 to 10,000 PSI to make certain that you are shattering your formation. But I've not ever read where I've got a sense of the pressure. I guarantee you if I'd read that, I'd be telling you what the pressures were, because I'd be impressed. So I don't know why that pressure is not mentioned. It's just always mentioned that they're using a lot of pressure to fracture the formation. But I think that pressure is entirely determined on the hardness of your formation.
Go until it gives.
Yeah. You see, they don't use this in western Colorado where you've got your oil. It's not, it's oil shale, but it's a real hard shale, and where they actually mine the shale, and they can't use fracturing there because that particular type of shale won't fracture, not like the East Coast Marcellus shale. I don't know how long this one is. Hang on. I started to view this, and I don't remember. I may cut this one off on you. Oh, this is Marathon's big advertising. I got frustrated with Marathon ad.
Geologists have known for years that substantial deposits of oil and natural gas are trapped in deep shale formations. These shale reservoirs were created tens of millions of years ago. Around the world today, with modern horizontal drilling techniques and hydraulic fracturing, The trapped oil and natural gas in these shale reservoirs is being safely and efficiently produced, gathered, and distributed to customers. Let's look at the drilling and completion process of a typical oil and natural gas well. Shale reservoirs are usually 1 mile or more below the surface, well below any underground source of drinking water, which is typically no more than 300 to 1,000 feet below the surface. Additionally, steel pipes, called casing, cemented in place, provide a multi-layered barrier to protect freshwater aquifers. During the past 60 years, the oil and gas industry has conducted fracture stimulations in over 1 million wells worldwide. The initial steps are the same as for any conventional well. A hole is drilled straight down using freshwater-based fluids, which cools the drill bit, carries the rock cuttings back to the surface, and stabilizes the wall of the wellbore. Once the hole extends below the deepest freshwater aquifer, the drill pipe is removed and replaced with steel pipe, called surface casing. Next, cement is pumped down the casing. When it reaches the bottom, it is pumped down and then back up between the casing and the borehole wall, creating an impermeable additional protective barrier between the wellbore and any freshwater sources. In some cases, depending on the geology of the area and the depth of the well, additional casing sections may be run and, like surface casing, are then cemented in place to ensure no movement of fluids or gas between those layers and the groundwater sources. What makes drilling for hydrocarbons in a shale formation unique is the necessity to drill horizontally. Vertical drilling continues to a depth called the kickoff point. This is where the wellbore begins curving to become horizontal. One of the advantages of horizontal drilling is that it's possible to drill several wells from only one drilling pad, minimizing the impact to the surface environment. When the targeted distance is reached, the drill pipe is removed, and additional steel casing is inserted through the full length of the wellbore. Once again, the casing is cemented in place. For some horizontal developments, new technology in the form of sliding sleeves and mechanical isolation devices replace cement in the creation of isolations along the wellbore. Once the drilling is finished and the final casing has been installed, the drilling rig is removed and preparations are made for the next steps, well completion. The first step in completing a well is the creation of a connection between the final casing and the reservoir rock. This consists of lowering a specialized tool called a perforating gun, which is equipped with shaped explosive charges, down to the rock layer containing oil or natural gas. This perforating gun is then fired, which creates holes through the casing, cement, and into the target rock. These perforating holes connect the reservoir and the wellbore. Since these perforations are only a few inches long and are performed more than a mile underground, the entire process is imperceptible on the surface. The perforation gun is then removed in preparation for the next step, hydraulic fracturing. The process consists of pumping a mixture of mostly water and sand, plus a few chemicals, under controlled conditions into deep underground reservoir formations. The chemicals are generally for lubrication, to keep bacteria from forming, and help carry the sand. These chemicals typically range in concentrations from 0.1 to 0.5% by volume and help to improve the performance of the stimulation. This stimulation fluid is sent to trucks that pump the fluid into the wellbore and out through the perforations that were noted earlier. This process creates fractures in the oil and gas reservoir rock. The sand in the frac fluid remains in these fractures in the rock and keeps them open when the pump pressure is relieved. This allows the previously trapped oil or natural gas to flow to the wellbore more easily. This initial stimulation segment is then isolated with a specially designed plug, and the perforating guns are used to perforate the next stage. This stage is then hydraulically fractured in the same manner. This process is repeated along the entire horizontal section of the well, which can extend several miles. Once the stimulation is complete, the isolation plugs are drilled out and production begins. Initially water and then natural gas or oil flows into the horizontal casing and up the wellbore. In the course of initial production of the well, approximately 15 to 50% of the fracturing fluid is recovered. This fluid is either recycled to be used on other fracturing operations or safely disposed of according to government regulations. The whole process of developing a well typically takes from 3 to 5 months, a few weeks to prepare the site, 4 to 6 weeks to drill the well, and then 1 to 3 months of completion activities, which includes 1 to 7 days of stimulation. But this 3 to 5 month investment can result in a well that will produce oil or natural gas for 20 to 40 years or more. When all of the oil or natural gas that can be recovered economically from a reservoir has been produced, work begins to return the land to the way it was before the drilling operations commenced. Wells will be filled with cement and pipes cut off 3 to 6 feet below ground level. All surface equipment will be removed, and all pads will be filled in with dirt or replanted. The land can then be used again by the landowner for other activities, and there will be virtually no visual signs that a well was once there. Today, hydraulic fracturing has become an increasingly important technique for producing oil and natural gas in places where the hydrocarbons were previously inaccessible. Technology will continue to be developed to improve the safe and economic development of oil and gas resources.
Hill core now, right?
Huh?
They're hill core now, right?
Yeah, they are.
Yeah.
Well, up here they are.
Yeah.
Does that help a little bit?
Yeah, that's pretty good to be.
A little bit better understanding? Some of the things that I want you to know about is once you brought a well in, I was just deciding whether I was going to talk about this as far as completions or yeah. So on starting a well, a lot of times what you'll use is nitrogen circulation, and that'll be a case of literally bringing in, it could be through a coil tubing unit or something of that nature. Literally, your well itself, let me get out of here. Your well itself will have, you'll be down at the, you'll have different, as it mentioned in there, water and different things of that nature will be within the well itself. And a lot of times that well may have pressure from your formation, but it doesn't want to flow. It can't overcome that viscous resistance of the material that's in there. That can be old drilling mud, could be old leavings from developing the well, things of that nature. So a lot of times what will happen is you'll use an inert fluid that'll be a nitrogen circulation. You'll go down and you'll actually kickstart the well flowing. You'll go ahead and pump down your annulus and then up your production string and begin to circulate that well, circulate out all of the heavy materials that are there, clean the well out with nitrogen until such things. Sometimes if you're driving past, it's now BJ Hughes out north, where they have a lot of wireline equipment, all types of stuff out at the Rick Hinders Road. Sometimes you'll see a tanker sitting there and it'll look like it's steaming. What they're doing is they're evacuating off a nitrogen tanker. And that nitrogen tanker, they're literally letting it exhaust as it's heating up so that it doesn't build too much pressure. But what they do is they'll circulate that nitrogen, bring it back up, and begin to get the well flowing, and then they will go ahead and let either the oil, if it's free flowing, or the natural gas, if it's free flowing, will then begin to be pulled up into that flow. Then you go ahead and cut one off, and then go ahead and then you've stimulated the well and brought it online. They don't all just immediately start flowing. A lot of times they need stimulation to get going.
Yeah, I thought I was reading in there that you can actually introduce a drill down in there if it's too dense to get it re-going
You
again.
can, there's lots of
Yeah.
different ways. You
Production tube?
could actually do that. Common is nitrogen circulation, but you could actually do something of that
Yeah.
nature. It's not unlike your race cars, your real exotic race cars on an oval track where they have to push start them to get them moving because they don't have their own self-starter. Push start them to get them going, and then they take off and they're great. Well, it's the same thing with a well. It's what's so bad about, for example, when Chevron chose, because the volcano was erupting, to shut, in fact the state may have required it, But whether they chose to or whether they agreed to the state, because the state said to, they shut in all the wells in the inlet when Redoubt erupted in this last series of eruptions a number of years ago. And when they went to restart all their wells, a lot of them had, the gas wells had watered in. That means that they had water down in the wells that literally were keeping the flow from coming up. A lot of the oil wells refused to move because there just wasn't enough flow to overcome all of the adverse fluids that had built up in the well, and they had to do a lot of treatment to get a lot of those wells going. Now, they refused to pay the cost to get a lot of them going. When Hillcorp came in, they actually went through a lot of dewatering process, a lot of stimulation process, and they've actually got wells flowing now out of Swanson River that haven't free flowed for 25 years. And they've got gas wells flowing out at the Cave Beach field, and also gas and oil flowing out on the platforms that haven't been working wells in a long time, because they've gone through and stimulated those wells, worked with them, get them back up online, and they just felt like the cost was justified and have pretty much paid for all of that. Now, why do you say, well, why didn't Chevron do that? Well, Chevron tends to be like Exxon and BP. They look at the higher realms of production. They don't really want to mess with the lower realms of production. Kind of like the difference between a huge supermarket, like a Walmart superstore, and maybe a mom and pop M&M Bilo out in Kiski. Each one's got their corner of the market that they're trying to go ahead and address. And Hillcorp approached Chevron. Chevron said, yeah, take it off our hands. We don't have time for it. But it's a producer.
There were actually numbers in the book, if I recall, that the smaller ones will shoot for 100 million barrels, but the bigger ones won't touch those until they get to 300 million barrels.
Yeah, there's a big differentiation between your big companies and your small ones. Now, your big companies are having to relook at some things because a lot of those big oil fields are what they used to call elephants. Are not around like they were. So they're going into more of the dangerous places offshore and places where small companies can't drill. There's also well testing that takes place, and well testing would be into a small well test vessel, in which would be somewhat like a three-phase separator, and you would actually take your well, you would turn it into your test receiver, and you would check to see what your gas flow, your oil flow, and your water cut would be over a certain period of time, normally a 24-hour period. You'd actually time it. You would, in the old days, you would have had regular graphic charts that would have monitored it. Now they still use the charts, but now everything is also fed into a DCS unit where you can go ahead and monitor what's going on. Because you really want to see what your well is doing. And not only will you look at your flows, but while your flows are going, you're also looking at your pressure. And if your pressure is dropping off, what your reservoir characteristics are doing. And you're wanting to monitor your well so that you do not overproduce it. Does anybody remember what I said about overproducing? Overproducing is a bad thing. What happens when I overproduce?
You leave pockets.
I leave pockets of oil. I leave stranded oil in pockets that now can be produced at a very costly amount, because I literally have to go in and drill specifically for those. Okay? So what I want is to start that well flowing. When we're talking 20, 30, 40-year wells, ideally, we want to start things moving, and then we don't want to ever have to stop it. Once it starts, we want to keep it moving. It likes to move once it's started. And because it isn't just a little bit, it's the entire viscous mess down there will all begin to, as this begins to move, then everything will start to move. As we've got this lower pressure here where we're producing, then the entire mass begins to move. And as it does, it tends to have its own inertia that is wanting that entire thing to migrate. Think three-dimensionally now, and the whole thing's beginning to migrate, but if it stops, and I've got any kind of spot in here that's a little resistive, then it creates resistance here, eddy currents which create resistance. Now you might think, well, it's not flowing that fast. No, there's slow motion, but it's enough that it will stop flows, and then your well doesn't want to start flowing. Some wells don't want to flow, well, then you have to go from a naturally flowing well to a pump. We're going to get into that in just a little bit after we take a break, but then you have to start paying costs for secondary recovery, and that gets to be expensive. Up on the slope, they're using a lot of, still doing everything they can to try to enhance natural flow because you get a lot higher production rates. So we're going to be doing bottom hole pressure tests. We're going to see, we'll actually shut the well in for, this is when we're developing the well. And developing, we would want to see just what it's capable of. We may produce it for a period of time, shut it down for a period of time, restart it, see how much the pressure increases, decreases, and some of these things. And we'll be looking at development, productivity tests, well flow tests, potential tests. We may flow it at maximum and see what it does, so that we have all of these parameters, and then we can go ahead, the reservoir engineer will say, okay, from what I'm reading on all of the parameters that we have here, all of this information this is what we should produce. We'll set a choke in our tree. Y'all remember the chokes that we talked about last week? And we'll set that choke, and it becomes the operator's job to make certain that the choke is set correctly and the well pressures are maintained where they're supposed to be at.
Not too much, not too little.
No, and that's right. We want to, anything that we do over and above that, I think I'll talk about wireline units and all that stuff when we get into the next portion. So let's take about a 5-minute break. We're going to come back. We're going to move into secondary and tertiary recovery. So we've gone out, we've explored for our well. Let's walk through this a little bit and kind of recap some things. And we've explored for our well. We've gone out, we've done all of our seismic work. We were looking for a well, and we've found some potential places. We've gone ahead and put in the money for the leases, and we bought up some leases, and now we're beginning to drill. Or we've got the leases, we're bringing in a drill company, or actually we've got a drilling outfit, and so now we're beginning to drill. We started drilling for oil based on the exploration, the seismic work we've done, and we're drilling, and we actually hit some production wells. And so then we've gone through and we've, just like you saw the timeline, we've set those wells, we've begun to produce those wells, we've actually completed them, they're starting to produce, that's where we're at now. We've gone through this whole thing of production, or not production, we're at production. We've gone through exploration, and purchase and drilling, and then we've gone into completion, and we're now at a point where we're going to begin to produce. The best wells to produce are the ones that free flow. Okay, and I'm going to talk just a bit about free flow, and then we're going to talk about secondary recovery, because secondary recovery and tertiary, which would be your third level recoveries, are a big deal. Oil and gas coming out of a formation under natural pressure is the best way that you can have oil produced. And how that'll happen is I will have, let's go back and draw a picture here. Hang on, I think this is a good time for some picture drawing. The homework has got a lot about different, and we're going to cover this over this next day and on into our next class periods in between our quiz. There's a lot of diagrams and things I'm going to want you to know. And I've given half of the whole final oftentimes to be nothing but just identifying parts on diagrams. Lots of diagrams. So that's so that you recognize what you're looking at. And when you go out of here, you'll know what different types of well situations are and those types of things. So if I've got a formation, we'll do our classic anticline, because that's a nice easy one to do. And we'll say that we've got a base rock down here, and then we've got maybe we've got gas. We'll say oil. I drew too many. Let me get rid of one, and I'll just keep the bottom, and I won't do this one. Okay, so we'll say that we've got our base rock here, and we've got our capstone up here, and in between we have got a formation. We're going to call this an oil formation, and so we're going to say that we have water right along here, and then we've got oil coming up to about here, and then we've got gas up above. So this is going to be gas, this is going to be oil, this is going to be water. You guys are all familiar with this. This is all the stuff that we've been doing, right? Okay. If I have enough pressure pushing on this water, say this particular formation goes out some distance somewhere, and I have got pressure pushing in on this water. Same thing here. It's going to cause, that hydraulic pressure is going to cause my oil to have a pretty good PSI, okay? So that if I drill a well down into this, it's going to want to come up here and produce a blowout, if you will. But it's going to have natural pressure, because I've got, coming here in my formation, I may have way back over here somewhere, I may have some sort of an aquifer or underground formation of ancient water, or it's coming clear up out of a anticline here down through a syncline and then pushing up, and I've actually got or I could have some sort of a dome over here, or who knows what, and I've actually got a lot of pressure. I've got an interface here between my oil and my water, but I've got hydraulic pressure, just like a ram, pushing here, maybe this comes down and it's pinched out over here, so now I've got this tremendous pressure. That oil is going to reflect that pressure, and until that pressure goes away, that oil is going to want to produce in free flow. That's the term I'm looking for here. Free flow, okay? And as I begin to free flow, what will happen is, over time, my pressure will begin to drop. If this is a 10,000 foot well, I'm going to have, coming back down right here, on a 10,000 foot well, at the bottom of my formation down here, I'm going to have about 4,300 pounds. We'll just keep that nice and easy to think about. That means that if my formation is above that 4,300 pounds, or down here in my oil, if I've got we'll say 5,000 PSI, I've got just under 700 pounds of upward pressure wanting to push up this well, so I can still produce. And I'll be able to produce until the formation reaches that point. We call this an artesian well if it's a water well. We've got artesian wells all along both sides of the Kenai River. This little farm down here that, I don't know what they call themselves now. Huh?
M&M?
What's that?
Diamond M.
Diamond M.
Yeah.
Diamond M. It's the Martin family, and they used to have right alongside their house. They had an artesian well that flowed right out of the top of the casing. Scott Kraxberger, who taught here, used to be connected with the Kraxberger well drilling. That was his dad that had that business, and they brought in a well one time down by the Kenai River that they couldn't cap. 235 gallon a minute free-flowing artesian well right out of the top of the casing, blew out. It flowed like that for years. Free-flowing well. And so you can have free-flowing water wells. You can have free-flowing oil wells and gas wells. Gas is always going to be free flowing, but we're going to specifically look at oil. So as long as my formation pressure was above my standing pressure coming from the surface or my static pressure, I'm going to have a free-flowing well. But over time, what's going to happen is that's going to diminish. And if I were to draw a graph of it, what it would look like is something like this. And over time, my pressure would begin to fall off until I reach that place where it doesn't want to flow anymore. When it's when it's depleted, it no longer free flows. And I have to go into something that we call secondary recovery. Doesn't mean I have to put a pump in right away, but I am going to have to go to secondary recovery because it won't free flow anymore. In other words, if I drop that 5,000 PSI down, and I'll do it sooner than this, but if I drop this down and I finally used up the pressure and my well is now at 43.33, my formation is at 43.33, my static head pressure is at 43.33. What am I going to have right at the top of that casing right there?
Max good standoff.
That's right. Could I actually see the oil in the casing?
Yeah,
It just sit there, though.
Hmm?
It would just sit there, though.
It would just sit there. It wouldn't do anything. Okay? If I had 43.34, what would it be doing on the top of that casing?
Just a little bit, just a little.
A little bit over. If I had 43.32, what would it be doing? Get down about a little bit. I could calculate it all out. I'm not going to do that today. But that's what you'd be looking at. I want you to think about that because when the pressure starts to fall off, it is expedient for us to enhance the formation or the situation in some way to keep that well free flowing if possible. We do not want to have to go to a pump. Now I'm going to talk about pumps in a little bit, but pumps have fixed rates. If I can enhance the formation to flow at a high rate, I will produce a lot more fluid at a cost-effective manner. That's going to be a number of things. Let me list some of those out because they're all things that we're going to talk about. And then we're going to come back to our pumps because I don't want us to be diminishing pumpability or giving the pump jack the evil eye because there's a lot of good things about pump jacks. Okay, so I'll think of one, I'm sure, but there's
Somebody to give somebody a job.
there's a lot of jobs for pump jacks, I'll tell you what. Okay, so some of the things, if we started to deplete our pressure before we go to a pump, we would probably want to go ahead and have water flood or water injection. We're going to call it water flood. This is where we would actually be pumping water down into our formation. We'll cover that in detail, why water flood is a good thing. One, it's going to build pressure. There's other reasons. Okay, another one is we might have gas injection. Okay, gas injection is going to be the same thing. We're going to be injecting gas injection, not gas injection. We're going to have gas injection. That's going to be similar to water flood, but water flood has advantages over gas injection. They both increase formation pressure, but there's advantages. With water flood, I can actually move oil around. With gas injection, I'm just pressuring up the formation. Then I can get into another situation where I'm actually using gas lift. We'll talk about gas lift and how that also facilitates our secondary recovery. Then we start getting into tertiary recovery, and we can get into what's called miscible injection. And so I'm going to tell you that at Prudhoe Bay right now, they're using all four of these. to keep the wells flowing, because it's way cheaper to have wells that are flowing and just maintain your pressure if at all possible. And part of the reduction in reduction in the production is because you don't want to lose that formation pressure, you want it to keep flowing without having to try to go ahead, and so you reduce the flow, keep the pressure up so that it will still continue to free flow. Then you can start getting into pumps. Pumps can incorporate, let's do this. You can have ESPs. ESPs are electrical submersible pumps. You can have pump jacks, which are rod pumps, and rod pumps are a positive displacement pump. You can have, I'll just leave that alone. Then you can also have, along with rod pumps, there's both the you can have deep rod pumps and shallow rod pumps. We'll cover that. You can also have, along with rod pumps, you can have, would be called a, how do I want to say that? It would be a power oil type pump, hydraulic actuator pump. I'm running out of space. Hang on.
Henry, can we assume these processes would be done in the order of cost effectiveness?
Absolutely.
Yeah.
Very much going to be money driven. And so that's enough for me listing things out. What you're going to see is it's going to be, depending on cost effectiveness. Let's cover that for just a moment. Out at the Swanson River field, they have no water flood. Never have had. Does anybody have an idea of why they have no water flood?
No water?
Exactly. No water. What's the only water that they almost took? What's the biggest stream flowing through the Swanson River field? Swanson River. They put their eyeballs on the Swanson River in the early 60s. Said, you know, that would work really well for water flooding.
But
And that river almost went away. Think about that. No Swanson River. But then they said, no, there's not enough water, and the state of Alaska said, nah, I don't think so. And the feds came on, this is before EPA and all that. They almost gave the Swanson River away. And today you wouldn't have a Swanson River. It would just be a old dry stream bed. It would be a hiking trail. Or at least it'd just be a trickle, okay? But there's no water to speak of in the Swanson River field. It's worthy. Now, there was some thought of going out into the inlet and recovering water out of the inlet, treating that water and using it for water flood. And probably would have, except what's the biggest problem with the water in the inlet?
salt in it?
Turbidity. It's not so much the salt, it's the turbidity. It's got a lot of stuff in the water, a lot of silt, a lot of things. Used to be a lot worse. It's not near as bad as it was. 40 years ago, we had this thing called Lake George that used to dump up in the Chugach Mountains. I don't know if any of you ever read about that, but it used to dump periodically about every 3 to 5 years and come down the Connect River, and it would catch everybody just like this, like a big, huge, massive flood. And that glacial lake would dump, and when it did, it would raise the river in a matter of just hours. It'd be anywhere from where it was just sandbars to being 10 to 15 feet deep, and it would flow like that for days. And what would happen is it would wash this huge amount of glacial mud right down into the inlet. And the inlet would look as gray as Brad's coat for years. And it would start to clear up because that glacial silt tends to be very fine. It would start to settle out, and the tide tends to keep it stirred up. was starting to settle out, well, then Lake George would dump again, and down it would come, and it would get very turbid again. And so that happened periodically, and the inlet was just a gray, it looked like gray clay when I moved here. It was really nasty, and it was that way all the way between the Nilchik and Anchor Point. You'd have to go that far down before, below Anchor Point, you'd start to see fairly clear water. Well, now you see fairly clear water clear up past the Nilchik. Didn't used to be like that, and you can get clear water tides clear up to the platforms now. And that never occurred before either. But what happened is Lake George is not dumped in a long, long time. And because it isn't dumping, the theory is that the water is, all of that fine silt is finally starting to settle. And so it's enough that rockfish are coming into the platforms and beginning to colonize around the platforms, which they never did before. So water flood, gas injection was used extensively in Swanson River. Gas injection, water flood were both immediately started up at Prudhoe Bay. Gas injection and water flood especially was used in the inlet because it was cost effective. Gas lift has come in the last 35 years, 30 years. That is a whole different concept. We'll go into that. Miscible injection's only been in the last 10 years, and that is a huge undertaking that has been part of what's kept production up. You would not even think that it would be viable, but yet once you begin to look at it, it's extremely viable. And then you get into pumps. Now, pumps, we're using rod pumps out in Swanson River now, and you guys are seeing it from the air, you just don't realize it. I'll show them to you, and then you'll know what you're looking at. Hydraulic pumps are hydraulic actuated with hydraulic power well from the surface going down and driving a rod pump that's down below the surface. And then ESPs have become the method of choice in the inlet because you're looking at producing a high volume of fluid because the water cuts are so large. Does everybody know what I mean by water cut? That's where you would actually take you take a grab sample and you check, you run it in a centrifuge and you see how much water you're actually making in your crude on a per barrel basis. And it'll be cut at a certain percentage. And so a good percentage when I was on the Dillon platform was maybe 3 to 5%. That same Dillon platform today is somewhere around 80%.
Water to oil.
Water to oil. Lots of water. And so if you're going to still recover your oil, use an ESP, you move a lot of fluid, you dispense with the water, but you keep the oil. And so then, but that changes everything. Now what do I need on my platforms? I've got to pull all of my equipment off and put in big power generators so that I can run these pumps. And so, all right, so let's go ahead and go into some of this and see what we've got. But I want you to know that the rod pump is king, okay? Now it doesn't look like much, but you know, in any given day in the United States, about close to 500,000 feet, no, more than that, there's about 450 to 500,000 of these pump jacks producing oil around the United States on any given day. And somewhere close to 1 million barrels a day are being produced by all of these little pump jacks. Now, somebody can divide that out if they want to, but that's not very much oil per pump jack. And they're called, what are they called? What's the name?
Horseheads?
These are horseheads, but what kind of wells are these? Stripper wells. They're generally stripper wells. That means that all the natural gas is off of them. They're not really viable anymore, but there's oil in there. Now, I know that I bring this up in class. I brought this up in class previously. Who in here, if I give you a 1 barrel a day well, is going to turn me down?
Not me.
Why?
It's 42 gallons, do the math, a year, 365.
$65,000 a year.
Boom.
Yeah, say that again. Yeah, you're both saying the same thing, but say the money.
$65,000 a year, and you're getting, say, 10% royalty, that's $36,000 a year.
Yeah, and that's saying that if I own the lease, then it's just whatever preventative maintenance I'm doing. So nobody in here is gonna turn me down if I give you a 1 barrel a day well in your backyard?
Nope.
Everyone says, not in my backyard, they see those numbers.
And if I give you a 5 of them, where you're producing 5 barrels a day,
It's on.
or I give you 3 wells that are each producing about 8 barrels a day each, that's 24 barrels per day, 365 days a year.
We go to your dinner, Henry.
Yeah, at least a dinner. And that's right, we've got close to 500,000 of these wells that are producing about some of them don't produce a barrel a day. Some of them produce a couple of barrels a week. They don't produce much. They honestly don't. What they do is they produce, and then they shut it down so that the pump doesn't go dry. Then they let the formation set, and you know what happens? That oil moves in, it fills up the reservoir again, and then they pump for a day or maybe 2 days, and shut down, and then they let the oil come back in. They might only be producing 3 barrels a week.
So is there like a guy that drives around in his truck and checks on these once a week or something?
That's right. You've got, and we were just talking about that up here, you've got people that do nothing but go around checking stripper wells, because oftentimes in these little stripper wells, what you have is you have a little tank sitting over here. And this is producing into that tank, or maybe it's on a timer and it's coming on every 2 days, and it pumps and then it shuts down after 12 hours or 24 hours, and it produces into this tank. Then you got a driver that comes around, he picks up the oil, and then he goes and delivers it to some refinery because they're selling the oil. And so it's quite a business. 1 million barrels a day in the United States are produced in this way.
That's a trickle.
Hmm?
That's just a trickle.
Yeah, but that's amazing, that 1 million barrels a day. And so we're going to take a look at these. These come in all kinds of different shapes and sizes. Take a look at this. Let's see, we won't be right here. There's quite an assortment of, that was one. This is, here's another one.
I've never heard that term.
What's that?
I've never heard the term nodding donkey. I mean, I literally grew up with pump jacks and stuff.
Oh, yeah, you've got nodding donkeys, and you've got, hang on, I've seen them where they're all decorated. I think I've got a few pictures of them. Let me see if this one's gonna come up.
I remember when oil hit $145, $150 a barrel, and every pump jack that was ever stationary in West Texas.
Yeah, this one's in a farmer's yard, and this one's pretty good. This is visually, you can see quite a bit here. You can see, they look like a little horse. This is called a horse head pump also, but Jack used to work on these things, and you've got your counterweight in here. You'll have a small motor on it. This will go up and down. The reason you've got the curve here is so that as this is coming down, it keeps this in a straight line, and it doesn't cause it to vary or veer. And so this is your walking beam, kind of similar to the cable tool pump or drill rig, and then this will go up and down. Positive displacement. Who in here's ever pumped water in a campground? Exactly the same thing. It's only that this is on down under the soil, quite a ways further. If you take a look, let's see, 1, 2, 3. How about this one? Yeah, this one is in a fast food joint, Charlie's Cafe, or Curly's Cafe. This is a pretty good size, and they come in big sizes like this. I told you that they were pumping oil in Huntington Beach when I was going into McDonald's. You know, everybody's going, hamburgers, and I'm going, oil! Over there hanging on the fence trying to see what was on the other side.
I used to live down there, and they were in people's backyards fenced off.
That's
Just,
right.
What the hell is that? And it's a horse head pump.
That's right,
In their
and
backyard?
they were making money off of that thing.
Just little ones.
Yeah, just little ones.
Yeah.
Some of them are little tiny ones. Some of them are big, huge ones. They come in all kinds of sizes. This one's actually a nodding donkey. This one looks like a jaybird. They take and they beautify these things. I mean, only oil people would have this kind of sense of humor. You know? Huh?
Like propane tanks back home.
That's right. They paint up propane tanks and all kinds of
Like a
stuff.
cow.
Yeah.
Kidding me?
This one's pretty good size right here. This is actually a big one. I don't know who this is. This is some individual. Now, Swanson River had a choice of going to this kind of, this is a deep well. This is not a shallow well type. Shallow well type will just be small. They won't be very large. This one's actually pretty good size. What they've done instead of going to this type is they come, and I just show this to you because they come in all kinds of shapes and sizes. This is actually Swanson River. Here, I think Jack went out with us. This is about probably 5 years ago. I was able to land a tour for some of the oil and gas students. This is actually a belt-driven rig, and if you guys are flying over, if you look down near the river and then over near the, just north of the gas compression building, you'll see these. These stand about 50 feet tall, and this is your rod coming down, this is your belt. This belt comes over and down the other side, and it's driven. It's a great big huge belt that off of some gears in the back with a 150 horse motor. And what this does is this rod goes down to 10,000 feet, 10,000 foot long rod. And so then what you're doing is taking, it's called a long stroke, it's 30-foot stroke instead of just being a little short stroke like on your horse heads. And so then what you're doing is you're going down on wells that were not considered viable for recovery. They said, well, you know, what if we get one of these and we go down, we begin to pump, and we'll see what we can do. So they reworked a few wells, put a couple of these belt-driven deep well positive displacement pumps in. And on this particular one right here, they're pulling about 225 barrels a day.
2 miles deep.
2 miles deep. Is that worthwhile?
Sure.
Oh, absolutely, because they were pumping oil. 200, it was over 200 barrels on the average every day. And actually it doesn't, that goes.
Low maintenance.
Low maintenance. Maintenance isn't too bad. It took them a while to figure it out because they were having some problems with the maintenance part because they didn't really know how to operate it. But then they got it set. That's kind of interesting because the shaft going down that deep, you don't want that shaft rubbing. It'll wear pretty quickly. So what it does is it actually comes down and that shaft actually turns a 1/16 of an inch. It's on a kind of a bearing type system where it will,
Evenly wear.
it actually rotates so it has even wear. And then it goes down. And the only problem that they had was on some of the oil, they were getting a pressure drop coming through the perforations they were actually getting wax buildup, and they'd have to go through and flush with methanol periodically to clean the perforations out. I'll give you another picture here. Now this fellow's since retired, and but this gives you a view of right at the Christmas tree. This is at the top of the tree, and this is where it was coming down. He was talking about that turning a 1/16 of an inch. So here's your tree. This is coming through the swab valve. And then this was off into production, and then we were coming out at about 50, 60 psi and pumping. The belt had come all the way down at this point and was just on its way back up when it kicked and turned. And so this is what nobody in their years ago thought we would ever be pumping oil here in Swanson River. They said, well, it'll always flow because we've got gas and we've got gas injection and the wells will always free flow. Well, it became too costly to continue to pump gas down into the formation to try to go ahead and keep the wells free flowing. So the wells were just shut in, and that's where they said, well, you know what? We think that it would be worth our while to try this. And so that's become a pretty good tool. These are more reliable than the great big huge horse heads. They are a little bit more costly as far as maintenance. So let's take a look at a pump jack then. Just a second, I'll take this up just a little bit. So on your horse head, your walking beam, if you were looking at your casing, this would be your casing, this would be your annulus, this is going to be your production tubing, and then your sucker rod going down between it. And this would be an expansion right here of what we've got over here. These do not have a packer in them. If you take a look down below, I'm going to show you, they're going to be open all the way up. I'm going to have my production tubing coming down into my pump, and then I'm going to be open on my annulus all the way to the top, no packer. And then when I'm open all the way to the top, what's going to take place is I'm going to pull the gas off, which is what you saw in the Swanson River. They had oil going one way, they had gas going the other. And I'm going to pull that gas off, and then I'm either going to use it separately or recombine it with the oil. But I don't want that gas and oil mixing down here. I want the gas to break out of the oil. Why would I want that?
Pump will cavitate.
That's right. I don't want my pump cavitating. So in this case, where a lot of times I've got a packer in there to separate things, in this case, I don't want to separate. We're going to see the same thing with an ESP. We're going to have it open all the way to the top. I don't want that gas in the oil. I want it to freely break out, if at all possible. So in here, I'm going to have gas breaking out. I'm going to pull the gas off, and then I'm going to have my oil being pumped up, and it's going to be we've got the walking beam, the horse head. We're going to come down through our polished rod, the rod going all the way down through the stuffing box, and then the beam's going to be going up and down. It's going to be a slow operating motor, usually low RPM, so that and the entire mechanism is going to rely on a counterweight or for inertia, so that we are not having to put a lot of money into the as far as driving it. Now that relates all the way back to when it was steam driven and things, where you could have a low power steam and then go ahead and use the inertia of a counterweight to keep things going, so that you're not having to pay a lot of money out for driving it.
Is that gas going to redirect just on through vacuum? Through natural vacuum, see how your gas is deviating and then your oil is...
No, these are completely isolated from each other.
Okay.
Yeah, think it like this. This is my tubing.
Okay.
Think of it as one string coming up.
Okay.
My annulus, completely isolated.
Okay.
These two are, and I'm glad you asked about it.
Yeah.
So my annulus and my production string are completely unrelated in
Oil's
this
still in
case.
there and the gas is...
Yeah, and so I'm only going to have oil coming up my production string, and my annulus, think of it as a secondary tube. It's like I have two tubes. They have no intermingling here until I'm actually producing, if I put it back in with it. Not always will it be that way. It could be I'm taking the gas out elsewhere. Got it on some sort of compressor system. And in here, you're going to have a standing valve, your pump barrel, and you're going to literally just be moving oil up, positive displacement. You're going to be moving it up as your rod is going up and down, and it's going to be just like a water well in a campground. I'm taking water and I'm literally forcing that water up through the tubing until it begins to flow. Now, does that have a limit to it? Yeah, it does. You don't find these that will pump much faster than about 300, Jack? Would that be maximum?
I don't remember.
2?
I don't remember.
I know Swanson River was maxed out at about 225 on that great big belt. And they just said, well, that's as much as we're going to do, and it wasn't worth the money to try to go any higher because they had to go into a whole different system. And you get into mechanical limitations because you've got a lot of machinery moving in opposite directions and a lot of change in direction. It's not like a ESP where I can move a lot of volume because I've got rotating machinery. Here I've got mechanical limitations. I can only go just so high. Were you looking it up? No. Usually sometimes I have people checking me out. And so anyway, I have not heard of any that produce much more than about 250 to 300. And that's, yes, sir.
The other thing that I do remember is they had 3 different ways of powering those. If they had electricity, they powered them with an electric motor. And they also had the guys that made their circuit every day and they would check things. Some had motors where they actually had gasoline or diesel when they powered them. And then others was plumbed right into the gas stream.
Off the gas.
Off the gas, and they run their engines periodically, self-starting and stopping.
We did that on the platforms. We
yeah.
ran all our Waukesha's off the natural gas.
Yeah.
You had to have special spark plugs. They were 3-prong spark plugs instead of your normal 1-prong. And so they were really clean and efficient. They could be temperamental when you wanted to start them. But otherwise, they ran great. I used to tear them down, put them back together. Yeah, so you could do that right here, and you'd have your gas that you're pulling off that maybe you couldn't sell anywhere. Thank you, Jack, appreciate that. And I could have this back on a driver that's driving instead of using electricity.
Your own gas tank.
That's right. Producing the oil, using the gas, producing here, and as slow as these things move, there's very little wear and tear. As long as I keep them greased up, the only thing that's going to bother them is an occasional tornado.
Another thing the farmers used to like when the pipes went through their fields, they would put buckets underneath little leaks in the pipes and they'd collect the drip gas.
Yeah.
And they'd run that in their tractors.
I worked with little guys who used to do that. So let's take a look at a hydraulic downhole pump. This is, I said, hydraulic pumps, and I'm going to try to explain this as best I can. This is actually a, they still use these on the platforms, and this was before gas lift really kicked in. So down below, you can have a turbine, jet piston, like on some of these real shallow water wells. But more commonly, what you have is between your hydraulic driver that's being driven off of your power oil, off of your motor up above, what you'll have is you'll have a driver and you'll have a pump, and they'll be connected by a rod. So in essence, it's really a rod pump, is what you're doing. But this hydraulic actuator, what you do is you literally will take, and I used to operate these, and so what you will actually do is you will take power oil, which is going to be crude. I'll explain the startup in just a minute. And you'd have a high pressure pump that's going to then go ahead and pump this power oil down you'll have this coming down your well in your annulus, and then it will be coming into your driver, and then your driver you'll be pumping that in it'll be a positive displacement hydraulic actuated pump that would exhaust into your tubing string, but at the same time you're connected by this rod which is actually driving a pump, just like we saw with the on our rod pump. And so then instead of having a 10,000 foot rod like Swanson River does, we would be using power oil to go down, and on a short rod, a short system here, we would be pumping oil using this power fluid to actuate it hydraulically, which then causes the pump to pump, and then both of the fresh oil and the power oil commingle, come up. We separate out enough to keep power fluid in here, and then the rest of it then becomes production. We used to pump down hole at anywhere from 4,500 to 5,600 psi, if that gives you some kind of idea. Lots of pressure.
That'll move it.
And then it would take, and they were extremely good. Let me explain this. One, if on that big, long, deep hole rod pump, Swanson River was having to bring workover rigs in to change out the rods on that because they were so long and so heavy. Okay? They had not found anybody that had the tools to work on that type of a system yet. In this system, I don't even have to have a wire line. All I have to do is I go through what we call a reversal, and I change the way that the fluid is going down by reversing it here, and I actually will cycle that pump. And that pump and that hydraulic power actuator and the pump will actually cycle all the way to the top. I will put a catcher up here. It will catch it, then I can isolate it, I can pull it, I can work on it, put my catcher back on top, cycle it back down, comes down into a shoe, and then it will take off and start pumping again. And so I've worked on many of those, torn them apart, put them back together again. And they still use these on the platforms, and because they're inexpensive to use, they're fairly efficient, and you're using your own oil as the driver. The only thing that you have to do is have a motor that's strong enough to run a pump. And so it's a lot like running an ESP. The only limitation here is you have the limitation of how much fluid you can actually move. Okay. They do operate at a higher speed than, especially if you get into the jet, piston, or turbine type, they do operate at a higher speed than the just a regular rod pump. These are called hydraulic actuator pumps. And so I would like you to know what those are. So nobody has asked, well, how do you get that power fluid in there if you haven't produced any crude yet? You know, good question, huh? Where does that come from? Well, what we did is we actually would take some of our diesel, where we would have somebody bring crude out from some other place. You have to have something to start with.
Prime it?
To prime it.
Right.
You literally have to have fluid to prime it, and you can't use water. You've got to have some sort of an oil. So you may have to buy some oil, you may have to bring crude in from another facility, and then you actually have to, or maybe you've got a well that's producing, and so you come off of that well. You have to have something to prime it. Once you prime it, you're good to go. You don't, but it's only when you originally start. You don't ever throw the prime away. Okay? Hydraulic actuator. This is called a secondary recovery. Hydraulic actuator pumps. ESPs. This is an ESP. I would like you to know this diagram. I'll give you another picture of an ESP. That would be like right here. This is literally an ESP. This is a good diagram of one. This shows you on the well casing. So what you're going to have is you're going to come down with your cable and your production tubing, and it'll set down in here. You'll have your pump assembly, your discharge assembly coming down into your, you can have a packer down below, depending on what you've got as far as where you're drawing from. You've got your motor, and then you've got your pump assembly right in here, and then on up into your discharge head and up your packing. This will be your cable coming down. This will be what you're setting in as far as drawing. Let's go to a real simple diagram, because I want you to know this diagram and keep it nice and simple for you. I would expect that you'd be able to label this entire thing. And so you'd have a motor, you'd have your cable going to the top, think extension cord, and that's exactly what you have here. You're going to have an equalizer, you're going to have an intake, you're going to have your pump, you're going to have your oil coming in, and as your motor begins to turn, it's going to go ahead and crank just like think water well, and you've got it right there. This is nothing but a water well. When you've got your electric cable going down into your well, it's exactly the same thing. A little bit different though, because these particular motors can be 200 feet long, 4 inches around, and be 200 or 300 horsepower. Weird looking little electric motors, but they can be extremely powerful, and they can move a lot of fluid. If I'm needing to move fluid, and I'm doing it in a cost-effective manner, suppose I'm moving 5,000 barrels a day of fluid, but I'm also making 500 barrels of oil out of that, okay, that being a low percentage of oil, or maybe I'm only making 100 barrels a day of oil out of that 5,000 barrels of fluid, that's still 100 barrels of oil. Maybe even at 50 barrels of oil, it still is almost effective to move 5,000 barrels of water and fluid. So this is where a lot of the industry is going. If Prudhoe Bay ever gets to the point where it becomes too expensive to run a lot of their secondary recovery, they'll probably go to this next.
Is that the equalizer to combat the torque, or what's the purpose of the equalizer?
I think it's more on the torque equalizer.
Okay. In other words, I think you just want to twist it. So.
Yeah, so that you don't end up breaking something internally within that. And so these are really good because what does head pressure do to this? Not really much. It becomes something that I look at, but there I'm more concerned now with my drawdown, like I would be on the water well, my drawdown this way as far as how far am I drawing that fluid down, am I over pumping or overproducing my field. So I'm going to go ahead and measure that with how much fluid I've got coming in, what my drawdown is, so that I don't start drawing down dry. If I start drawing down too much, I can leave stuff back in the formation. What we've run into on the platforms, though, is a lot of platforms were built for hydraulic production and water flood production. Water flood's gone away, hydraulic oil has gone away, ESPs have come into play, so that meant that a lot of the infrastructure that was on the platforms were being pulled off and are bringing in generator systems, and a lot of them are turbine systems now because they have gas available, and so they're bringing in these small turbine units that will produce a megawatt of power or a couple of megawatts. You put a couple of little tiny solar generators, solar turbines with generators, and you can produce 1 to 2 or 3 megawatts, and you've got enough power to run a lot of ESPs. And so that has tended to be the way a lot of this is going. So the entire industry and infrastructure in the inlet is changing. A lot of folks don't know that that's what's really taking place. They just know that there's a lot of activity. A lot of the activity is because of the change in the infrastructure and what's going on. So let's keep going. Here, I'll show you. When we talk about if I go to put in an ESP, that means that I've got to change my wellhead. Why? Because what do I have going down my well? I have an electric cord. I have a great big extension cord. Up at the top, I've got this great big plug-in. No, I'm just kidding. And where do I plug this in at? You know, a big 3-phase cord. So I have to change out my wellhead. It isn't just as easy as just putting it in. I've got to come up with a whole new wellhead that's going to allow me to make an entry through that wellhead and bring that cord down into the well, where before I had integrity, now I've got a place that has got a possible leak potential. Didn't have that before. Okay, so that's something that I have to think about. The other thing I've got to think about is, consider this. Let's go back and look at this, because I think I may have lost some things on this. If I've got this particular system hanging in my well casing, how do I change that out? Suppose my ESP decides to have an electrical problem and I have to pull that and change it out.
Can you do it with a wire line, or do you have to put it in a workover rig?
Can't do it with a wire line. I have to pull the whole string because that entire thing is hooked to the bottom of my well. So I want to make sure that when I put that in, I have got a good running system that's got good integrity going down, so that once it's in there, it's going to operate for a long time. Anybody in here ever pulled their water well?
I see them do it.
Anybody ever do it by hand? Did that too. I did it once, and after that I almost lost it.
It's a lot of footage to yank.
It's a lot of stuff, yeah. And so just our little tiny wells that we have and pulling them up, we went to plastic pipe after we had the iron pipe. Iron pipe got all ate up and everything, but that's still a lot of weight. And so you have to go in with a workover rig. And so that tends to be expensive. This also shows the entry point right here for the electric line coming down and through. And so this becomes a potential place for leakage right here on your production. but then you would bring it on down through, you'd change this all out, this would be part now of your wellhead that wasn't there before.
Well, how much pressure are you creating at the top of that well? I mean, theoretically, we're not dealing with any formation pressure, so it's a little safer, and then you're just dealing with whatever pressure the pump is creating.
Yeah, and it could be anywhere from 1,000 to 1,500, 2,500 PSI. Something that's gonna bring it up, all the way up. I've still got that 4,300 PSI of resistance coming back down at me.
Right.
So I need enough that I can push that up and overcome that. When I say that, I can have discharge pressures up that high.
Right.
But normally, it's just going to be enough that I've got discharge pressures where I'm moving a lot of fluid. And, so, yeah, regardless of, I've got my static head pressure.
Well, you may have 4,000 pounds at the bottom of the well.
But I don't at the top.
Yeah, you only need 1 pound of pressure at the top.
That's right. And then I begin to move fluid. So it's going to come down to how much fluid I want to move.
Right. Okay.
It really is. We have enough time to talk about this next part. Actually, it's going to take me some time to talk about this next part. 25 minutes. I got 25 minutes. All right, you guys ready? Water flood. Water flood is a whole different characteristic. We talked about water flood being where let's go back to our formation right here. Okay? So we had this ugly formation. Let's draw us a new formation, and this is what we're going to see. Okay. You guys remind me when I got 5 minutes to go. Okay, so here we go. This is a good anticline. We'll use the classic anticline so that we can take a look at this right here. And we're coming down through, and we've got our well that we're producing out of. Okay, we'll just make this well like so. We're down here. And what we're doing is we're going to go ahead and we're going to put in water flood. We've got water across like this. We have a little tiny gas cap up here. We're going to address that in just a little bit. And then what we've got is we're producing oil. But we've lost all our pressure, so we said, okay, you know what? We're going to put in a water flood unit system. We've got lots of water around here. And so we put in this other well, and when we do, we put it in like so, and we go ahead and we come right down into our water, okay? And we begin to pressure up this water. We're increasing the pressure. And as we do, we're increasing the pressure in such a way as it's beginning to push like this. Okay, now I want you to think in terms of we are increasing the hydraulic pressure in such a way as it's causing this oil then the formation to increase. We are actually increasing the production in our oil out the top of our production string, where maybe we'll go to the 10,000 foot well, we had fallen down to say 4,500 PSI in our formation, and our production was down pitifully. We were just producing a little bit of oil. So we began water flood. There's a couple of benefits on water flood. One, as we begin to pump in here, we're increasing the pressure. So we came up from 4,500 to say 47, 48, 49, 5,000. We're increasing pressure. That's obvious to everybody. Well, let's look at something else that happened. Let's take a look at another view. This is going to be a top view. Okay, so this is our oil field. And what we do is we're looking from the top down, and we are looking at the oil formation, and we realize that what we need to do with our water flood is we've done test wells. We've gone around and we've done a test well here, here, here. We've done a demarcation. We've checked our wells, and this is how we came out with our design. We've realized that this is actually the boundary line for our oil field. And so we go, you know, what we should do is we should go ahead and put our wells in such a place. We're going to put our water flood wells, we'll put one right here, and we'll put one right here, and we'll put one right here, And what we'll do is we're gonna put in new oil wells, and we'll put those right here and right here. And we'll just have these things drawing really hard. And what we're going to do is we're going to begin to help this oil to migrate towards these wells. So that we begin to, maybe we're gonna put one more water flood well right over in this area, and we literally begin to do a situation where on a front like this, we are helping to herd, if you will, we're helping to move that oil. We're not only pressuring the formation, but we're helping to sweep that oil as through the rocks as it's going. Anybody here ever clean a floor where there's oil and stuff, and you're causing that oil to go ahead and move? Now you're going to leave a residue in the rocks. We'll talk about that miscible injection. But here, if I have good accurate placement, this is only looking at two-dimensionally looking down, but three-dimensionally from the side, I would also be looking at what depths I want to put it in and that type of thing. And then what I do is I'm beginning to help that oil to migrate. Why would I do that? What am I trying to avoid?
Pockets.
I don't want to leave any pockets back there. It's no oil molecule left behind.
Why wouldn't you want to put your wells at the opposite end and just force it all over?
Well, I could,
And try-
but expense-wise, it may be that I want to start here, and maybe this has always been the high production zone
Okay.
over here, and I'm wanting to start cleaning this out. Now, once I start this, then this might be in the first 2 years.
Okay.
The next few years, I might want to start in here. The next year's in here because it's going to be costly, first off. But I don't want to just hit and miss, put one here, here, and here. That's not going to serve any purpose. Those formations are huge, some of them, a lot of volume.
But you've just shown us where it is.
Mm-hmm.
Why wouldn't you put your water pressure on the east side and force all the oil over to the west side where your wells are?
Oh, you're talking about over there, pushing it all this way?
No, where you're at, but put your wells over here and force it all over there.
Oh, I could go ahead and this might be the case here. This would be the first layer. Second, this would be the first system. Next one then, okay, this would be the first year. First year drilling program.
Okay.
Second year drilling program, I come along, we're gonna say this is the second year, and so then what I'm doing is I'm going ahead and putting in some more wells here to go ahead and trap that oil as it's coming along. Not clear over here, not clear over here, but catching it as it's going so that I don't leave any oil behind.
Okay.
Well, wouldn't the middle be your peak?
Huh?
Wouldn't the middle be the peak?
It would be if it's a, now I was assuming a pancake formation, but you're right. Okay, so if I'm looking at hold on, we'll just redraw this. If I am assuming I see what you guys are driving at. If this is an anticline right here, okay, then I would start it on that side, and then over here, the second year, I could do it 1 year or the other or both, but then I would start in the same way here, and then I would probably come along and I would start in with all of my, just a second, I drew that. This should be black, 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 like that. I could have blue right here and herd it this way, this way, this way, and catch everything here, so where I'm going like so. And then as I begin to go, then I could come along and I could go ahead and put in some pretty good wells like this, so that by then I have cleaned this entire area out here. I've left nothing back there, I've left nothing back here. I could start working on this side and this side, and I'm pushing everything in this direction one step at a time until I finally come down to this spot right here. One layer at a time. Think three-dimensionally. Yeah, God, what an awful mess. But you don't want to take off more than you could chew when you're, how do you eat a whale? Well, one bite at a time, okay? And you can consume the whole thing, but you cannot swallow the whole thing at a time. So what you have to do is, it wouldn't do me much good to just set these here and start pushing from clear over here, because I may end up losing my motion. So what I want to do is I want to make sure that I've got something that's drawing this oil as I'm moving until I get to that place where I finally arrive and I've not left anything back here.
Yeah, plus wouldn't it, if you tried to just kind of either force it all in the middle in one shot or all on one side, it would take too much water or too much of whatever you're injecting down in there
To move it?
to move it all the way to the
Yeah,
other
and the
side.
Saudis learned this the hard way. What they did is they started putting in, and this is going back on some of the stuff they learned on the Galar field, they started putting in big wells and big injections and stuff, and they said, it's really weird, is our water's going in, but we're not seeing it anywhere. And what happened is there were cracks in the formation that they didn't know
Absorbing.
about. And it was absorbing
So they're losing all their,
potential.
right.
Completely. So then they said, you know what we need to do is we need to back up and start taking it small portions at a time,
I get that.
work on, say, on just this section, so we don't leave anything behind here, this section, and then push.
That makes sense.
And so that's, no, you had a good idea, Steve, and that's really how it
I'm
started
thinking
off.
too small though is what I was doing.
Yeah, and so really what you wanted to do is you go in, and then economically, this actually works more feasibly, because then what you do is you take a little bit at a time, you begin adding in, okay, I've got that infrastructure in, now the next infrastructure, I see how my reservoir is responding that first year around, then I go ahead and plan, because then I need to see what I have. I'm assuming that my geological structure is consistent all the way down underneath. It may not be. This is another thing the Saudis ran into and others. It wasn't consistent all the way through. And so they found that they had different permeability when they didn't realize that they did. And so it's a matter of moving it and recovering it, and so that's what you would have. Does that, everybody grasp what I'm talking about there? Your reservoir engineers get into this, and there's been some real changes over the last, after watching what the Galar field, largest oil field in the world, and then also what the Mexican government did with their Cantarell field and the destruction of that field, and how to and how not to work an oil field. Also going back to the West or East Texas oil field and the kind of recovery that has gone on in that when it should have died about 30, 40 years ago, and it's still a high producer. A lot of those things have been implemented with Prudhoe Bay, and that's why Prudhoe Bay is still a producing field and going to be producing for another 30, 40 years at today's technology. You guys need to try to explain that to your family.
Oh, I've got the picture, that's the Henry diagram, that's what.
Did you take a photo of that?
Yeah.
That's funny. Okay, so let's go ahead and take a look some more at what we're talking about here. So then when we get into water flood, this is what we're looking at, is we want to move that water over in such a way, we want to create a force, if you will, that's not only pressuring the formation, but causing the oil to move in front of it. A water flood is fantastic for, I call it herding oil, but it's fantastic for moving oil on a combined front, three-dimensionally, okay? And whereas gas won't do that. Gas injection, you push gas down here and all it's going to do is begin to pressure the formation, but it won't necessarily move the oil in a combined front like this, whereas water will, because water will begin to displace the oil, and along with gas, then you can pressure up the formation with gas, and then use water to begin to move that oil, especially if you've got some way of creating a low pressure sphere over here where that oil wants to go to that location. So there's two ways of doing that, is I can use gas lift here to create a low pressure spot, or I can use an ESP or something like that that's creating a void, and so that oil then is wanting to move. We don't think much about those pressure differentials, but it doesn't take much pressure differential for it to want to move. if we're patient under the ground. It will move, and it doesn't take a lot. It just takes a difference in pressure. Here, we've got force, here we've got something less, and so it's wanting to produce, and it will produce without having to have a pump on it.
Pushing and pulling basically at the same time.
Yeah, it's kind of a push-pull thing, and so works pretty well. So let's take a look. We've got another. Whoops, I had another. Just a minute, I'll put that, call it up a different way. So this is another way of looking at it. This shows how you can put your water down and have different water wells. And here, what we're doing is we're literally moving. We've got a production well, we're moving it, and if we're not careful, we could end up with some oil that is stranded because we're causing a void with water in here. That's why you have to be real careful where you put these wells so that you begin to move that oil where it needs to go, and at different, this shows the three-dimensional, and at different levels, not just looking at the top, okay, I want to put it here, here, and here, but also at the top, but also at the side, and also, like Ben brought up, the type of formation. What kind of formation is it? Where is it most expedient for me to put those water injection wells, and at what level? Okay? And this is what you would be looking at when it comes across. It's going to begin to displace that oil, and then we don't end up with stranded oil that is left in the void. Stranded oil is expensive oil.
To get to, yeah.
It's lost
Get it
oil
out.
that can't be readily drilled for. So, I think I'll stop here. That's enough on water flood, and the next part goes into some more things. So, grab the homework there, and next week we will probably be taking the quiz and talking some more.
Probably or for sure?
For sure.
What's that? No, the quiz is next week. There's no review, right? The review is at the house.
Reviews at the house.